It may appear simple for a human to navigate through a crowded environment, but when that environment is a mix of physical obstacles, other humans, and animals that may be going wherever they want and at the speed they want, mixed in with vehicles that may or may not have the right-of-way, navigating through buildings, along sidewalks, streets, open fields, swamps, mountains, and so forth, maybe things start to get a little more complicated. Now consider that we want autonomous vehicles or robots to navigate the same space and cohabit that space with all the other entities. And also consider that perhaps it is not just one, but multiple robots that may be working together, or independently, or against other robots and humans that may have their own agendas. This highlights the complexity of the situation. The assumption is that we will expect these autonomous systems to operate according to acceptable policies that guide their behavior. The purpose of this work is to create and test the policies before they are released into the real world. One could deploy self-learning techniques such as artificial neural nets with genetic algorithms, where the robots learn through trial and error. This would likely lead to the destruction of numerous robots, vehicles, and humans, not to mention the environment in the process. It would also be costly and time-consuming, and would likely result in delaying progress in the field. Using these self-learning techniques, the robots could learn what they wanted and make up their own rules. One could also attempt to hard-code the robots to respond to every possible scenario. This too would prove to be too expensive and lead to mountains of unmanageable code. This effort will demonstrate the use of a policy test platform that will be used to evaluate KEEL Technology-based policies that tells the robot how to interpret what it observes and how it should react. Rather than attempting to create and extend policies as the need arises, this effort will focus on creating an environment that can quickly expose the policies to a wide range of challenges and observe the response for analysis. The platform has been produced in two forms, one that can be executed on a web page and another as a desktop version. The web page version, for safety reasons, is limited to modeling the environment in which the autonomous system might find itself. This version does not allow the user to load policies for testing. The desktop version extends the web page version and allows problem scenarios to be captured and reused. The desktop version also works with policies created using the KEEL Toolkit. The KEEL Toolkit policies can be loaded for evaluation without going through any software compiles, thus saving time and effort. The policies can then be tested against the various problem scenarios. First, a brief view of the web page version. The vehicle is represented by a wheeled vehicle graphic and came from a simulation environment. In this case, however, the vehicle is stationary and the obstacles can be moved and reoriented. The Add button allows you to add obstacles to the screen. Once they are added to the screen, you can drag them around the screen as they might appear in your test scenario. At this point in the development cycle, 4 different types of obstacles can be added. When you first add an obstacle to the screen, it is added as a mobile object. This would be like another vehicle or a human. These types of obstacles have heading, speed, and importance or significance characteristics. When you click on this obstacle and move it around the screen, it becomes the selected obstacle. You can change its characteristics by selecting a radio button and adjusting the value with your mouse roller button. At this point, we have added a mobile obstacle to the screen and adjusted its heading and importance and speed. This is the information that the ground vehicle might observe if it is in the line of sight of the vehicle. The gray circle surrounding the vehicle represents its range of view. At this point, the mobile obstacle is shown in front and to the left of the vehicle, and it is shown moving from the left to the right. The length of the arrow on the front of the obstacle indicates its speed. The size of the red ball is an indication of its importance. Now I will add another obstacle to the screen. This time I will select the stationary checkbox, indicating that it is to be a stationary obstacle. I can drag it into position and adjust its importance. The thought is that some obstacles may be more important than others, and perhaps there is some sensor system that can recognize this situation. Now I will add another obstacle. The add function duplicates the selected or the most recently added type of obstacle, so it duplicates the stationary object I had previously added. I am unselecting the stationary type and changing this new obstacle to a mobile parked obstacle type. This is represented by a blue ball. This type of obstacle has heading and speed characteristics. I can move it on the screen to configure my test scenario. Now I will add a fourth obstacle. I will change this one to be a barrier type. This is shown as a line to indicate something like a wall that my ground vehicle cannot navigate through or see through. A barrier type of obstacle has a heading or angle and a length. I can adjust these to create my operational scenario that the ground vehicle will have to consider when it needs to decide how to handle the situation. I will add another barrier obstacle just to make things a little more interesting. You may notice that the text box in the upper right corner of the screen is being updated as I add obstacles to the screen and move them around. This allows me to see detailed information on each obstacle. One of the issues of any simulation environment is that the computer sees everything, and what we are trying to accomplish is to expose the vehicle to only what it can see, not all of what the computer can see. So a lot of the work of this policy test platform is to hide much of the information from the ground vehicle. At this point, we have 5 obstacles, and we can see their details here. Now let's look at more information as we attempt to provide only appropriate information to the ground vehicle for analysis. The concept of left and right from the vehicle's point of view is important. The Option 1 checkbox shows arrows to the left edge of all obstacles. Point obstacles, mobile, mobile parked, and stationary, have left and right sides at the same point. With Option 1 checkbox selected, we are showing more information about the vehicle's view. We are showing left and right information, and we are showing when some obstacles are behind and out of view from the vehicle's perspective. Other checkboxes show information more graphically. The objective is to show alternative path options that the ground vehicle will have to consider to determine what to do. Option 2 shows arrows to the left and right sides of paths between obstacles. Option 3 exposes some of the mathematics needed to determine if an obstacle is hidden. Option 4 shows the heading that the ground vehicle will have to navigate toward in order to traverse a particular path. Option 5 shows arrows for each of the paths that need to be considered. This information collectively will be provided to the KEEL policy to establish a value for each of the paths. The path with the highest value will be selected, unless it fails to reach a defined threshold value. In that case, other alternatives will have to be considered, like stopping and waiting, or backing out and trying some completely different approach. This completes our introduction to the web page version of the policy evaluation system. Now I am switching to the desktop version of the policy evaluation system. The desktop version allows the application to make use of the Windows file system as well as the Windows clipboard. It is important to recognize that the policy evaluation platform is still a work in progress. It will be expanded as necessary to simulate more features that are important to the path interpretation process. The purpose of the desktop version is to allow the user to load policies that are created with the KEEL toolkit into the policy evaluation system where they can be tested to see that they provide the desired functionality. It has the added feature of allowing complex scenarios to be saved and recalled, a feature that was not possible with the web page version. When the desktop application is started, a few new buttons are displayed. The Copy Screen button simply copies the screen image to the clipboard, where it can be pasted into your word processing system for documentation purposes. The Load button allows you to load previously saved obstacle scenarios. The Save button allows you to save obstacle scenarios. The KEEL button allows you to load the KEEL policies into the system that are created with the KEEL toolkit. So let's put the system to work. First, let me load a previously stored scenario. This information has been saved as an XML file. In the future, we may have simulations that can capture their observations in this structure so they can be loaded into the policy evaluation system for detailed behavioral analysis. This scenario has 4 barrier walls. The vehicle desires to go straight ahead through the top of the screen. Using the checkboxes we described for the web page version, we can expose the different options. We can see that there are 3 potential paths that have been identified. Now I want to switch briefly to the KEEL toolkit, where I have created a very simple policy for path evaluation. The present policy evaluation system has placeholders for 10 characteristics that might be used to evaluate one path against another. Presently, only 4 of the 10 characteristics have been implemented for interpretation by the KEEL engine. Distance ahead of the vehicle, distance to the side of the vehicle, path width if the path is between 2 obstacles, and point distance angle. The point distance angle is the optimal angle the vehicle would have to pass through in order to navigate between obstacles. This policy design has not been developed to the extent that it weighs these characteristics differently or collectively. It is just there to show that a KEEL engine has been created and has been saved to disk. Now I am switching back to the policy evaluation system. Next, I want to load the KEEL engine I just showed you into the policy evaluation system. Once it is loaded, a new KEEL checkbox is visible. When I select this option, the KEEL engine starts processing what the vehicle observes and determines which path, if any, is the best option. The result is displayed in the text box, along with how it determined a value for each path. To show that the vehicle is continuously evaluating what it sees, you can move the obstacles around and observe the response to the change. Here I am moving the barrier obstacle 2 to the right. This exposes a new path that the vehicle didn't see before. It quickly reacts and determines this new path is the preferred option. So to summarize, the KEEL toolkit provides a means of quickly creating policies that can interpret information and make decisions and control actions. The policy evaluation system is being created to evaluate those policies that might tell an autonomous ground system or robot how to address stationary and dynamic obstacles as the vehicle moves around in pursuit of its objectives. Once the policies have been validated in the policy evaluation system, they can be deployed with minimal effort in broader simulations. Once they are tested in simulations, the KEEL toolkit can be used to auto-generate the code that can be integrated into the target autonomous systems.